Hi, welcome to the frequency response of a common drain. The technique that I'll be using is the open time constant analysis. It's a technique that I've read in the Thomas Lee book, and it might be in the Cedra Smith book as well, but that's the place where I've seen it. When you use the open time constant, basically what you want to do is you want to use a small signal model. Okay, and once you use the small signal model, you want to use a test voltage VT and a IT test current, and you insert them where the capacitors would be. And what you want to do is you want to do a VT over IT, which gives you the resistance that the capacitor would see at that particular spot. Okay. Once you do that, next step would be, since you have the capacitance and you have the resistance, that gives you a time constant, a TC. So basically what you're doing is you're calculating the time constant. Okay. Once you have all the time constant, then you just plug it into this formula, which will give you the approximate bandwidth, and it's basically 1 divided by 2 pi, and it's the summation of all the time constants. Okay, so each time constant will be a particular capacitor. In this case, it could be a CGS. The next one could be a CGD, and there's other capacitors. I believe there's a C, G, and a bulk, and I believe there's one for the bulk as well. Now I'm not using these in my simulation. We'll be using just the CGS and GD to simplify the analysis, make it a little bit more easier to follow. Okay, so next would be the small signal model. This is a small signal model. Okay, and if you can see from the model, you can see that I have the capacitance from the gate. That's the gate, source, and this would be the drain. Okay, and like I said, there's, I believe, 4 capacitors, but I'm neglecting the other 2, and I'm just concentrating on these 2. Excuse me. Concentrating on the gate to source and gate to drain. This is also known as the Miller cap. Is another name. Okay, so once you have that, I'll go ahead and go with the analysis, or how to calculate it. And the first one I will do is the analysis for CGD. Okay, we go ahead and use a little bit medium. Let me adjust this. Okay, this capacitor or this resistor would be your R gate, and where the first capacitor or the gate to source capacitor was, we'll go ahead and leave it open. Okay, and in this case, this is where CGD was. It was connected from the gate to the drain. Okay, and if you look up here, the drain is connected to, in this case, the drain is connected to ground, because when you do a small signal analysis, the sources are grounded. So since that is the source, that is grounded, so that's why you ground that. And in this case you have a bias, that would be a bias, so that's grounded as well. So you end up with this model. Okay, so now I'm going to go ahead and put this in red. Since you put a test voltage across the capacitor, it will develop a voltage, or not a voltage but a current, that flows in this direction, and that would be IT. Okay, and let me go ahead and put the ground. Okay, so in this case what you want to do is you want to define, typically you would define your VGS, but in this case, since this is grounded, okay, and you look at the V gate, okay, if you notice the voltage at the gate would be IT times R gate. Okay, and it would have that type of sign. Okay, now if you notice, since this side is grounded and the positive, the VT, is connected to G, you can say that VT is equal to V gate, which is equal to IT. Okay, so we can rewrite it like so. And we can bring the IT to the left, and we can see that the resistance that C, G, and D sees is actually R gate. Okay, so in this case we can go ahead, we can say that tau is going to be R gate times C, G, D. So that's pretty simple. Okay, so now let's go ahead and do, just bear with me, let's do CGS. Okay, so the circuit should look something like this. There should be R gate. Okay, and instead of putting a capacitor, we'll put a test voltage. Here's the current, which is GM. Okay, and I'll put V just for right now. And that's grounded. And this would be your R load. Okay, so again, let me label this. This would be the gate, drain, source. Okay, the test voltage that I inserted where CGS would be, develops a current again, goes in this direction, that's IT, develops a voltage across the resistor, so you got that. Okay, now if you notice, this is supposed to be VGS from here to here, So we can say by inspection VGS is actually VT. Okay, and typically this would be GM VGS. So instead of writing VGS, oh, let me go ahead and write it VGS, but then say that it's GM VT. Okay, so we have that so far. Okay, and then what we can do a KCL at the source. So let me go ahead and write that. We'll do a KCL of the current loops. So basically you're going to have this current coming in with, which is GMVT, and we have IT going out. So we will label this, or at least I can label that as IX. Okay, and typically the convention that I use is if current is leaving, I set it as a positive. Any current that is entering, I go as a negative. So I'll go with the negative first. I'll say it's 1 negative GM VT plus IX plus IT equals 0. Okay, so we go ahead and solve for IX, which means that should be GM VT minus IT. So I can go ahead, since I already know what this is, I can say that this current going through the R load is GM VT minus IT. Okay, alrighty. Okay, so I have these two equations. So let's go ahead and define VT. And you can define VT as, and instead of writing V gate, I'm going to put VG. That would be VG right here. Okay, let me go ahead and just say that this is VG VS. Okay, so VT is going to be VS. Okay, so now what is VS or VG? VG is actually IT times R gate. Okay, so now let's find out what VS is. Okay, in this case it's positive and negative, so we know that the current going through R load is actually GM VT minus IT. Okay, so now we're almost there. So now we can say that VT is equal to, like I said before, it's VG minus VS. So we can say that it's IT R gate minus R load times GM VT IT. Okay. Alrighty, so I'll go ahead and let me go ahead and do the algebra and get to the answer. Okay, I went ahead and did the algebra. I expanded it then I collected the VTs. Here's the VT, and then there's the ITs on the right side. And when I bring it all together and do a VT over IT, this is the resistance that CGS sees. Okay, so now we calculate the time constant, which is CGS times our gate, our load, 1 plus GM, our load. Okay, then we can, let me see if I did this up there. Time constant. Okay, so I have it in the time constant. Okay, so now we put everything together. The bandwidth then is 2 pi times tau 1 plus tau 2. Okay, now I'm going to go ahead and do a SPICE simulation. Okay, and the parameters that I'll be using as far as CGS is 124.7 picofarads for the gate to source, and for the drain, or actually gate to drain, will be 3.3 picofarads. Okay, and I believe the numbers, excuse me, let me add some more. The resistors that I'll be using is 5K for the gate and 100 for the source. So let me go ahead and write that down. So our gate is equal to 5K ohms, and our load, let's see, I forgot, it's 100. Okay, there'll be 100 ohms. Okay, the only thing that I need is GM. Okay, now GM I can get from the SPICE simulation, or I can calculate it, but I don't feel like calculating. I'll let SPICE calculate it for me. Okay, and actually I believe I have it calculated. It's here. If you look at the output file, it has a GM of, it should be 0.605. so GM 0.605. okay, now if I plug all of that into MathCAD, I have our gate, our load, and I have the capacitor from gate to source, gate to drain, and then I plugged in GM1. Okay, and of course the unit is amps per volt, and here's my T1, tau 1, which is our gate times the capacitance from the gate to drain. Okay, and that gives you a time constant of 16.5 nanoseconds. Okay, and if you want to, you can plug this into the 1 divided by 2 pi and tau, and gives you a frequency. So it tells you that CGD has a break point of 9.6 megahertz. Okay. Now we do the same thing for tau 2. Here's the resistance that the capacitance from gain to source sees, and tau is 10.3 nanoseconds. Okay, you plug it in, it's about 15. However, these two are not the real frequency. Okay, the real frequency is when you plug both taus. So here's the bandwidth, which is 1 divided by 2 pi, and then it's the summation of tau 1 and tau 2. So in this case, the frequency response of the common drain should be 5.9 megahertz. Okay, so here I have the simulator. I enabled the AC response, and I'm doing a frequency response from 1 to 10 gigahertz with 1,000 points per decade. Okay, and I labeled out, that would be my out, and I put this SPICE directive with the pound autoplot AC, meaning that it's going to be an AC analysis, and we have to put VDB, that way it plots it in dBs. Okay, so we go ahead, press run, and this is the gain. Okay, now the gain or the bandwidth is where you have your negative 3 dB intersection, or it's when your gain drops by 3 dB. So if you look here, I have x2 and minus, I'm sorry, y2 minus y1. So as I go up in frequency, we notice that the frequency or the delta increases. So I can go ahead and keep incrementing this until I get close to 3, and there it is at 3. And if you look in here, it says 5.9, so that would be 5.90 megahertz. Okay, and then which should agree, or at least it's very close. The open time constant predicts 5.9 megahertz. SPICE says that it's 5.90 megahertz, which is pretty good in agreement. Okay, now I do want to give a little bit of a caveat that this is a very good way of estimating bandwidth. However, the only issue is that you're typically, the resistance of the gate has to be typically greater than R load. Okay, and when I say greater than, typically if you have anywhere, if your gate is 5 times or greater, then the simulation results are very good. They match up very well. If these are equal, then the open time constant doesn't work as well. You get errors in it. Now, this technique was developed for ICs, and typically on a gate, or actually on a common drain, would be connected, let's say, to a common source, and this gate resistance would be very, very high. So in those cases, the OTC would actually, the open time constant would be a very, very good way of analyzing the frequency response. Anyway, if you have questions, email me. If there's a request for the SPICE or the MathCAD, you can email them to rbola35618 and drop me a line, and I will send you the SPICE and the MathCAD files. Thank you for watching.